Welcome to Maths with EJD. In this video, we'll be talking about two-way ANOVA. ANOVA is analysis of variance, of course. Previously, we had considered one-way ANOVA and the Python code for dealing with that. I mean, it's when it comes to ANOVA, things can get uh, really tasking when it comes to computation, but then the Python code makes things pretty easy. So this, of course, you can expect it to be longer than the one-way ANOVA. But I mean, after this video, I'll also take the Python code for this, and then for the other two types of ANOVA, I'll just go for the Python code straight instead of trying to compute manually. So let's go for this. Talking about two-way ANOVA. So two-way ANOVA, that is analysis of variance, is the statistical test that allows you to examine the effect of two categorical independent variables. Two categorical independent variables, or what you can call factors, on a continuous dependent variable. So here you have a continuous dependent variable, but then you want to see the impact of two categorical independent variables on it. So, of course, we should remember that ANOVA is one of the parametric tests. Okay. The only thing is that compared to the other tests like t-test and z-test, this one can take into account three or more groups. So this analysis, that is the two-way ANOVA, this analysis is particularly useful, is particularly useful for evaluating the interaction effects, the interaction effects between factors and understanding understanding how each independent variable influences the dependent variable individually and in combination. So, for instance, you want to look at the effect of nutrition and genetics on growth, right? So, here now, you want to see how nutrition alone affects growth, how genetics alone affects growth, and how did both of them in combination jointly affect growth. So that's the kind of idea when we come to two-way ANOVA. So let's go to talk about some concepts and terminology. Concepts and terminology. Okay, so let's start with main effects. Main effects. Okay. Um, in two-way ANOVA, you analyze the main effects of each factor, of each factor, of each factor, or what you call the independent variable on the dependent variable. So each main factor, each main effect rather, each main effect is the average effect of one factor. Each main effect is the average effect of one factor, ignoring ignoring the influence, ignoring the influence of the other factors. So when you neglect the effect of if you focus on how one factor impacts the independent the dependent variable and you ignore the effect of the other factor, then it means you're considering the main effect of that factor you're paying attention to. So then we go for number two. There's also the interaction effect. Interaction effect. So the interaction effect is when the effect of one factor on the dependent variable on the dependent variable actually depends on the level of the other factor. Okay. So the interaction effect is when the effect of one factor on the dependent variable depends on the level of the other factor. So this is key. This is key to a two-way ANOVA, as it indicates whether the factors have combined effects. Okay. Then, okay, let's talk about factors and levels now. Another thing to talk about under two-way ANOVA, the factors and levels. Factors and levels. So, for instance, if you have like factor A, for instance, you're considering a teaching method, you're considering teaching method as factor A. Okay. So factor A might factor A might have levels such as method one. Under teaching method, you have method one and method two. So the factor is teaching method, but the levels, I guess I want to change this to something else. Okay, let's go for this. So the factor is the teaching method, but the levels are method one and method two. In this case, then you have factor B. Factor B, you can also have factor B, which will be class type. Okay. So you're looking at the effect of teaching method and class type on maybe student performance or something like that. So factor B, e.g., class type, could also have levels, could have levels like lecture and lab. So those are, the settings for the instruction. So the type of class, is it a lecture or is it a lab? The method of teaching, the teaching method, is it method one or method two? That's the kind of idea there. Okay. So you have factor A, factor B. And then, so that's talking about factors and levels now. Then we also need to know that in two-way ANOVA, you analyze all all combinations, all combinations of these levels to evaluate evaluate the impact of both factors on the dependent variable variable, which might be something like test scores test scores. So in this setup now, you want to see how the teaching method and class type affect test scores. And just like what we've seen here, you have to combine them. So what if with teaching method one with lecture, teaching method one with lab, teaching method two with lecture, and teaching method two with lab? So those are like four different combinations. How do they impact the test score of a student? That's the kind of thing we want to consider in ANOVA. So finally, we talk about the dependent variable, which we have been introduced to just now, talking about test scores. So dependent variable, okay. So here, the outcome variable you are measuring, the outcome variable you are measuring, that's the dependent variable. So example, in our example, this would be this would be test scores. Okay. Now let's talk about some assumptions of two-way ANOVA. Assumptions now. So one assumption is the independence of observations. We assume the observations are independent. They have nothing in common. So this is to say each observation should be independent of the others. That is one assumption. Another assumption would be normality. Normality. And what this simply means is that the dependent variable, the dependent variable should should follow a normal distribution for each combination of factor levels. Then, number three, we talk about homogeneity of variances. Homogeneity of variances. So the variances are homogeneous. So this tells us that variance, variance within each group, variance within each group combination, variance within each group combination should be approximately equal. Okay. And then we have the fourth assumption is about random sampling. Random sampling. Okay. We're talking about random sampling now. We have um that the data should data should come from a random sample. Data should come from a random sample. Okay. Now that all of that is done, let's take a situation. Let's look at steps. What are the steps for conducting Steps for conducting a two-way ANOVA. Okay, and I'm going to do this with example. So as I mentioned the step, I'll take an example straight because I know this can be pretty long if I'm not careful. So actually, let's walk through a detailed example to illustrate the steps in conducting a two-way ANOVA. So um let's look at the kind of scenario we're considering, which has been stated previously even. So the scenario is this you want to consider a examining examining the effect of teaching method, which is factor A in this case, factor A, and class type, which is factor B, class type, that is factor B, okay, on students, students' test scores, which is your dependent variable. Okay. Okay. So, um, then we have, let me just go here. We have factor A, or let me color code here. Uh, let me color code here. So we have factor A, which is teaching method, which has two levels. Okay, it has two levels. So it has two levels. The first level is teaching method one. You know, you can call, maybe it's even as a specific name, you can do that. So, and the other one is method two. So those are the two levels for factor A. Okay. So it can have more than two levels actually, but let's leave it at two for now. Then we have factor B. We have factor B now, which is class type, which is also in two levels. It can actually be in three levels. You know, in the actual educational setting, right? You could actually have things like maybe you can have class type in three levels. Say you have okay, well, if you have two levels, we can say two levels. The first level is lecture. The second level is lab. So we can have a third level like group study. So, but I mean, here we restrict this to two levels. Okay. Now, for simplicity, for simplicity, assume assume we have a sample, we have a sample of test scores. Okay. I mean, just to emphasize that that is our dependent variable. We have a sample of test scores from 10 students, from 10 students per per combination of factors. Okay. Uh, so I mean, let's assume the following test scores. Let's assume, let's assume the following test scores. Okay, say um mm, I'm trying to see what to do here. Okay, now before I do this, right, let's go for the steps and then I bring in the table and start working already because this is quite a task. So let's look at step one. What step one involves in two-way ANOVA is calculation of the group means. Calculate the group means. Calculate the group means. Okay, that is step one. So let's assume the following test scores. So it means you're going to have a combination of factors and then walk through it like that. So imagine we have teaching method, we have class type, and we have the test scores. We have test scores. Of course, like I said, the first step is to calculate the group mean. So we can go for the mean straight up. So let's start the step that way. So imagine for teaching method, we have method one. Okay. So now, once we have to combine across groups. So we have method one for lecture. Let's see how that works. We have method two, still method one rather, for lab. Okay. Uh, so that's method one taken care of that way. Okay. Now we can also have method two. We have to combine them in pairs like that. Um, Say you now have method two for lecture again, method two for lecture. So a method two again for lab. Okay. So um I mean, if I'm going to code this, I can say something like okay, let me just do the coding here. Say this is method one is one here, method two is two here, method one, lecture is one, two, lab is two. So what I simply mean is, so for the combinations, like the combinations can now be something like one, one, okay, one, two, all right. So one, two, then we can have two, one, two, two. So that when you have one, one, you're saying method one lecture, and one, two is method one lab, then two, one is method two lecture, two, two is method two lab. So let's follow it that way for easy comprehension. So let's say the test course. So after somebody who has been taught using teaching method one in a lecture with lecture format, and the test scores at the end of the day would be this 5, 80, 85, okay, 85, 78, 91, 87, and 90. Okay. And then okay, I guess okay, let me just go on. So for method one in the lab, they got 88, 84, 92, 89, and 85. Okay, that's for method two. And for method one lecture in the lab rather, method two in the lecture format is this test scores are 75, 80, 78, 82, and 77. And lastly, for method two in the lab setting, the scores are 83, 88, 81, 86, and 85. So like we said, we need the mean for each of these groups. We need the mean for each of these groups. So for each combination, we actually have 5 test scores. So here now it means we have 81, 85 plus 78 plus 91 plus 87 plus 90 divided by 5. So the mean here is 86.2. And for the next one, we have 88, then we have 84, then we have 92, we have 89, and then we have 85. So that's 88 plus 84 plus 92 plus 89 plus 85 divided by 2. Divided by 5, that is 87.6. So that's the first step, right? Calculate the group means. The next, we have 75 plus 80, 75 plus 80 plus 78 plus 82 plus 77. And that is 78.4. Then lastly, we have 83, we have 83 plus 88 plus 81 plus 86 plus 85 divided by 5. 83 plus 88 plus 81 plus 86 plus 85 divided by 5. That is 84.6. So those are the group means. That's the first step we take here. So those are the group means. So the next thing we do after calculating the group means would be to see the next thing. Step 2. So we've calculated the mean score for each combination. Then the next thing, we have to calculate the marginal means. That's so under step 1, right? We calculate the mean score for each combination, which we have just done now. So the next is to calculate the marginal means. Let's see how to go about that. Okay. So group means done. So this is so just if you follow my calculation, right? This is more like if you like, you can call this X bar. Okay, this is X11 bar. Okay, X12 bar. Then this is X21 bar, and this is X22 bar for easy identification. So those are the means, right? For easy identification, we can have it that way. Okay, so that's step 1. We have calculated the group means. Okay, now let's go for step 2. So two, step two is to calculate the marginal means, the marginal means for each factor, for each factor. And what does that mean? We'll see that right now. Uh, so talking about marginal mean now, what's this now? Method 1 mean, method 2 mean. Okay. Oh, yeah. So marginal mean now, yeah. So calculate the marginal means for each factor. So now we say factor A, for factor A, which is teaching method. So it's more like calculating the mean on the broad level. So calculating the overall mean. That's what this simply means. So here now, which it means to just have so for method one mean. So method 1 mean is, you see, you take, this is X11 bar plus X12 bar, okay? Based on the coding we have done. So you add that up and divide by 2. So that is X11 bar plus X12 bar divided by 2. So the focus is on 1 here. We're talking about method 1, and that is simply 86, 86.2 plus 87.6. Or I can take that down for easy handling. So this is 86.2 plus 87.6 divided by 2. Okay, so that is method 1 mean. So if you like, you can let me call that M1 bar for the sake of to make things easy. Can I do that? Yeah. So method 1 bar. So this is, or better still, okay. I don't want to confuse things up like that. X1. Yeah, I guess I can call it X1 bar, right? We can call it X1 bar because it's the first factor. So for the second factor now, no, it's the first, I want to be sure because we still have for factor, right? If I call this 1 and call that 2 for method 2, what do I call the factors? Okay. Okay. So we can actually say we can have it like factor A. So we can say A1 bar. Good. I think that helps, right? That helps. So let's call this A1 bar. I just need a representation for this. So that's A, we can call it A1 bar. That's for method one now. So we now have A1 bar to be 86.2 plus 87.6. I mean, it's a long journey. So let's go carefully. So 86.2 plus 87.6 now divided by 2. That is 86.2 plus 87.6. Okay. So that is 86.9. That's 86.9 for method one. So that's factor A, right? So for method two, so method two mean now, method two mean, which I can call A2 bar. So that would be um that will be X12, if you like. Sorry, that's X21 plus X22. X21, X21 bar plus X22 bar divided by 2. And that is equal to, I think that should be 81.5, but let's be very sure. So that is 78.4, 84.6. 78.4 plus 84.6 divided by 2. So um 78.4, 84.6 divided by 2. When we add that, we divide by 2. So that's 78.4, 78.4 plus 84.6. 84, 84.6. That is 81.5. So A2 bar is 81.5. So we have that also. Then that's for factor A. We are talking about the marginal means for each factor. So it's more like take all the scores in each factor, add them together and divide by 10, or take the averages you have done already and divide by add together and divide by 2. So let's go for factor B, which is class type now. Okay. For factor B, that is our class type. Class type. Okay. So we now have lecture mean. Lecture mean. So lecture mean now is more like B1 bar. Okay. Because lecture is the first factor of the first level of of factor B. So B1 bar would just be X21, B1 bar. That will be B1 bar. Okay, so that'll be us putting together uh everything about lecture now. So that will be lecture here and lecture here. That's 86.2 plus 78.4. So everything lecture. So let's go for that. 86.2 plus 78.4. So 86.2 plus 78.4 divided by 2. Or you could as well just take everything lecture, add all the scores together and divide by 10. That it's the same thing you're going to get. So this is 86.2 plus 78.4. 78.4. And that is 86.3. So B1 bar is 86.3. Okay. Then we can also have lab mean. That'll be B2 bar. So that is, oh, okay, I forgot to write the formula for this. That is like, lecture mean is X11 bar plus X21 bar. So X11 bar plus X21 bar. Then for lab mean now, that will be X12 bar plus X22 bar. Okay. X12 bar plus X22 bar divided by 2. Okay. This divided by 2, right? Then X12 is 87.6, and then that's this and this now. 87.6 plus 84.6. 87.6 plus 84.6. Okay. So this is B2 bar now is 87.6 plus 84.6 divided by 2. So that B2 bar is equal to 87.6. 87.6 plus 84.6. 84.6 divided by 2. 87.6 plus 84.6. So that gives us 86.1. So that's B2 bar. That's the marginal means for each factor. Okay, so step 2 accomplished. So let's go for step 3 now. Step 3. So what we do in step 3 is to calculate the overall mean. The overall mean. So calculate the overall mean. That is all the 20 scores, you calculate their mean. Or another way you can go is to calculate the four means you have now. So you can actually either add up all the numbers, like all the numbers you have, you add them up and divide by 20, or the alternative is to add up all these four means and divide by 4, or better still, um yeah, I think that can work. Yeah, that should work. Yes, I believe that should work. So normally you add up all the numbers. So to calculate the overall mean now, so I mean that's to find the overall mean, add all scores and divide by total number of observations. Or the other thing you can do is, okay, let me say overall mean, which we can simply say X bar is, for me, that should be X11 bar plus X12 bar plus X21 bar plus X22 bar, all divided by 4. Okay, so that's X bar equals each of that. So that will be 86.2, 87.6, 86.2, 86.2 plus 87.6, I think 78.4, 78.4, 84.6, 78.4 plus 84.6 divided by 4. The alternative is to add up each of these 20 numbers and divide by 20. So 85 plus 78 plus 91, blah, 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 down to 85, and you divide by 20. But the easier way, since these ones are the averages of those four groups already, so add up the averages and divide by 4, you should still get the same results. So X bar, which is the overall mean, let's do that and see what we get. So let's go for that. We are dividing by 4 now, mind you. So let's go. So we have 86.2, 86.2 plus 87.6 plus 78.4 plus 84.6. So that we now okay. Okay. Let's see what. Yeah. So 86.2 plus 87.6 plus 78.4 plus 84.6. That is 84.2 overall. 84.2. That's you adding all the 20 scores and dividing by 20. You get 84.2. Okay. 84.2. Now, 84.2. Or should I take the pain of doing all that to be very sure? Okay, let's try to confirm. Let's try to confirm. I want to be sure There's no mistake of any sort. But I think that's actually correct. So let me go pretty fast if I can. Um, so this is like, this should be a long one already. So this is 85 plus 78 plus 91 plus 87 plus 90. Don't forget we are adding 20 things, so we have to divide by 20. Then plus 88 plus 84 plus 92 plus 89 plus 85 plus 75 plus 80 plus 78 plus 82 plus 77 plus 83 plus 88 plus 81. Okay, 83, 88, 81 plus 86 plus 85 divided by 20. Okay, that's 84.2. So that method is also correct. So 84.2 it is. Now we have calculated the overall mean, and that is step 3. So step 4 is the next thing we have to do. Step 4. So for step 4 now, step 4, calculate the sum of squares. That is step 4. Calculate the sum of squares. So here we're calculating the sum of squares. Okay. So here we are going to have of course, we already know we are in for serious computations. Okay, so let's start with the first sum of squares. So we have the total sum of squares, which is SST. And, this measures, it measures the total variability, in the data. Okay, it is calculated as the sum of squared differences, between each observation, and the overall mean, Okay, that is the sum of squares total. So, and this is computed as SST equals summation from IJK, summation over IJK rather, of XIJK minus X bar squared. Okay, now that's the formula here, sum of squares total. And how do we compute that? So this is how we go. So we know the overall mean is 84.2 already, right? Okay, what I'm just going to do is, instead of going through all the stress, so we just say that here, let's just say here, SST is equal to, okay, each value up there, each of the 20 values, so this would be like 85 minus 84.2, okay, squared, okay, then plus, then I'll just take the first ones. So 85 minus 84.2 squared plus, that's for method 1 lecture, 85 minus 84.2. So the next will be 78 minus 84.2 squared. The next will be 91, but I'm just going to take the first one in each combination. So 85 minus 84.2 squared plus the next will be 88 minus 84.2 squared. That is that. Of course, there are things in between that I've skipped. I've skipped 4 in between. So I'm just taking the first of each combination. Then the next will now be the first of method 2 lecture, that is 75 minus 84.2 squared, plus, okay, I mean, there's a space, that there's a gap there. Then between this and the last one, there are also another 4. So I take 83 minus 84.2 squared. But then I'm going to, in my computation, right, I'm going to do everything so that to save space. So after this, you still have 4 going. Okay. So that means you take each number, 85 minus 4.2 squared, 88 minus 84.2, I mean 87, 78 minus 84.2 squared, 91 minus 84.2 squared. But I'm just jumping. That's why you have all these things in between means that I've skipped values because I'm just taking the first value of each combination. But in my computation, I'm going to do everything and then I'll just return the final answer. So let's go for that. This is such a journey. So let's keep moving. Okay, so and then when you do this, if you have to do this in an exam, in fact, if you have this in an exam situation, by all means, try to avoid it. Okay, let's try to avoid it. But if you cannot avoid it, you need to be very careful because you can make mistakes easily. So let's go. I have 85 minus the overall mean, that's 84.2 all squared. Okay, all squared. So then I have to keep going that way. So the next one is okay, now 78. So I have 85. The next is 78 minus 84.2 all squared. The next one is 91. 91. So I have 91. Then plus that's 91 minus 84.2 squared. Then the next after 91 is 87. 87. Then the next is 90. 90 minus 84.2 all squared. 90. So this is a lot. This is a whole lot. So after 90, we have 88. So 88 minus 84.2 squared. Then, I mean, you're prone to making mistakes, so you have to be extremely, extremely careful. So after 88, we have 84. So 84 minus 84.2 squared. 84 minus 84.2 squared. Then the next one is 92. 92. 92 minus 84.2 squared. Next, we have 89. 89 minus 84.2 squared. That's 89 minus 84.2 squared. Then I have 85. That's just half way. 85. So then I have after 85, we have 75 now. 75 minus 84.2 all squared plus the next one. After 75, we have 80. 80. Then after that, we have 78. 78. Okay, plus again, after 78, we have 82. Okay, we are going gradually. 82 plus this again. So after 82, we have 77. Okay, 77 minus 4.2. Then after that, we have 83 minus 84.2 all squared. 83. Okay. And then wow, it looks like I've been copying and pasting. Now it's looking like I can't do that anymore. Okay. Can I do that now? Okay, so I have to keep going. After 83, right, we have 88 minus 84.2 all squared, plus, okay, I can paste again. So after 88, I have 81, 81, After 81, I have 86. 86 minus 84.2 squared. After that, finally, we have 85. Ah, this is serious. So 85, thankfully. So we need the answer to this. But I mean, let's run through again and be sure. We have 85, 85, 78, 91, 87, 90, 88. Okay, 85, 78, 91, 87, 90, 88, 84, 92, 80, 80. After 92 is 89, okay? After 89, we have 85, and then 75, 80, 78, 82, 77, then 83, 83, 88, 81, 86, and 85. Okay, so we need the answer to this. Yeah. So the sum of squared total is 453.2. That's a lot, 453.2. So that is the sum of squares total. Okay. All right. So that's sum of squares total. Now let's move on to the next sum of squares. We are going to have a couple of sum of squares. The next sum of squares is going to be sum of squares for factor A. Okay. That's the number two. Factor number two now. Can we say sum of squares? Sum of squares for factor A that you can call SSA. Okay, sum of squares for factor A. And what would that be? So this measures the variability. It measures the variability due to due to differences due to differences in levels of factor A, which is teaching method in this case, right? Factor A here is teaching method. Okay. And what is the formula? It's simply SSA, which is equal to summation over I of NAI into XA. Did I for factor A, right? I think I just did X. So since it's factor A, right? So I think I did X1I. Or better still, I could have said XAI really. Okay. Um, yeah, so let's just say X1I minus X bar all squared. So this is sum of squares for factor A. So let's see how we compute that. Sum of squares for factor A. Sum of squares for factor A. So what this simply means is that SSA, SSA, SSA now will be it should just be N overall N multiplied by X11, minus X bar squared plus X12 minus X bar all squared, okay? Like this. Or better still, I can say XA1 or XA2. Say, just know what you're using. Now, from what we've done already, right? Of course, we have N is 10. So 10 observations, that's N. Okay. So N, we have 10 observations. So N is equal to 10. Then you remember that okay, this is X11 bar, X12 bar, sorry. So X11 bar, if you remember, that was 86.9, I believe. x11 bar. Okay. X11 bar. Okay. I think this is actually A1 bar. A1 bar. So yeah, A1 bar and A2 bar. So it is 6.9 and it's 1.5. That's what we need here. Uh, okay. I think it's important to use exactly what we used there. Um, this is serious. Let me just follow what I have done up there so you can follow easily. Okay. So I mean I called these ones X. This is actually like this is AI AI bar. Okay. That's what I called it. So this is AI bar. This is A1 bar now, and this is A2 bar, like what we had. And then this is so for A1 bar now. So we know A1 bar is equal to 86.9. And A2 bar, that's for factor one, right? That's 81.5. So, and that's all we need. Then X bar itself is the overall mean, which is 84.2, 84.2. So, I mean, this should be easy to compute. So we just know that here, our SSA is equal to 10 multiplied by 86.9 minus 84.2 squared plus 81.5, 81.5 minus 84.2 squared. So we can easily get our SSA now. So SSA, let's go for that. Um, SSA now, we have, okay, let me just go times 10 times 86.9, 86.9 minus 84.2 all squared plus 81.5, 81.5 minus 84.2 all squared. Okay, so we get the results. So SSA is 145.8. So that is that is sum of squares for factor A. Okay, 145.8 sum of squares for factor A. Of course, we have to do sum of squares for factor B, as you can already imagine. So this is 145.8. So for sum of squares for B now, so you can follow the same idea. That's number 3. Sum of squares for B. Sum of squares for B. Okay. Number 3. Sum of squares for factor B. That is SSB. Okay. So here, this measures the variability. It measures the variability due to differences, in levels of factor B, which is actually class type in this situation. So, and the formula is something like this. SSB is summation over J of N NBJ, okay, into what I called B1 bar. I think that was what I called it up there. Yeah. So we had B1 bar and B2 bar, 86.3, 86.1. Okay. So that is B1 bar, or rather, let's call it BJ bar minus X bar all squared. So that's the formula right here. Okay. So for implementation, that means SSB is simply 10. I mean, sorry, let's just expand n times n times okay. This is actually okay. I mean, I could just, what did I do before? This is NA1, right? So this is okay. I think the idea should have been A NAI, okay? NAI. And here, this is NAI. So NAI is 10. That means they don't have to be the same. So here we have NBJ, okay? They don't actually have to be the same. So that simply means that, okay, NBJ, right? So if we come here to implement to do it, so it means we have NBJ. That's the number of observations for factor 2. It doesn't have to be 10. It's only here. I mean, in this case, we just have it that they are both 10 each. They don't have to be whatever they are. That's what we have to use. So here we have B1 bar minus X bar all squared plus B2 bar minus X bar all squared, like that. Then interestingly, NBJ here is 10, like NAI, which is okay. So we need B1 bar, B1 bar, and B2 bar. B1 bar, like I said before, B1 bar 86.3, B2 bar 86.1. Okay. B1 bar 86.3, then B2 bar is 86.1. And then of course, don't forget X bar is always 84.2. That's the overall mean. So that is what we are in for here. So let's do that. Okay. Now we can say that SSB is equal to that sum of squares for factor B. That is 10 times, that's 10 times summation of 86. Okay, yeah, squared, of course. So 86.3 minus 84.2 squared plus 86.1 squared. Okay. Sorry, 86.1 minus 84.2 squared. Okay. So that SSB, we can get the answer in one blow. So let's go for that. It's really close to what we had before. So it's only that we now have 10 times 86.3 all squared plus 86.1, 86.1, 86.1 minus 84.2 all squared. So we can get this also. This is 80.2. So SSB is 80.2. Okay. SSB is 80.2. Then, apart from SSB, we now need to get SSAB. That's more of some kind of interaction thing now. So that is um number 3. So let's do the fourth sum of squares. So number 4, we need SSAB. Okay, let's go for SSAB. SSAB. Now this is a long one. I mean, it's over an hour already, but it's okay. Just do it once and make sure it's correct and it's on record. SSAB is the next thing we need to look for. So let's go for it. That is sum of squares. Sum of squares for interaction. That's interaction between factors A and B. Sum of squares for interaction. That is SSAB. So sum of squares for the interaction between factors A and B. Okay. So this actually measures the variability. It measures the variability due to the interaction rather between factor A, that's teaching method, and factor B, class type. Okay, so that we now have so SSAB now, SSAB would just be summation over I over J of Nij into X. I'm wondering what is, okay, let me just write it. I may have to change it based on what I already told you. Xij bar Xai bar minus Xbj plus okay, yeah, I get it. Plus X bar all squared. So absolutely, I'm going to have to change something, but let's see what I have to change based on what I already, I had my own notation for these things. So let's go for that. Um, okay. So we're talking about SSAB. So here now, SSAB, sum this and multiply by n. Okay. Um, for method one, okay, 86.2. Okay, now I'm trying to, let me list out these things. Okay, um, so we have to do, we have to do the combination 1, 1, 1, 2, 1, 3, and so on and so forth. Okay, so I'm trying to be careful to get this right. Okay, um, okay. Yeah, I think this should still work. This should work. Okay. You remember my grouping the first time, right? So we have to do it across those groupings. So I think I'd rather um just do it that way. Yeah. So the only thing is that I guess this have got to change. So I think this is what's gonna change now. This is what it's gonna change now. So this is just gonna be AI. Okay, this will be AI bar, then BJ bar. Then every other thing is okay. So AI bar is that like A1 bar, A2 bar, and B1 bar, B2 bar. Then XIJ, I think it still aligns with what I did the other time. So it means if we, okay, this is a formula here that we are going to use. So instead of having to break it down, I think I'll just go through. Say we're saying that SSAB now is simply the same thing as NIJ. NIJ would be the, so I mean talking about the interactions, if you take them in pairs, right? They are 10 each. So trying to see this. Okay. So this is more like the NIJ thing is out there. So this is NIJ. So NIJ multiplied by, so we can now do all this. So this is the first one will be x11 minus x11 minus a1, okay, minus b1 bar like this, then plus x bar all squared. That's the first layer. The second layer would be x12 minus a1 bar minus b2. So you can see j is 2 now. So minus b2, okay, minus b2, then okay, plus x bar as usual. Then now carefully we have so back at this first level, we now have x21. Oh, that's bar too, right? It is also bar. X21 bar minus a2 bar, okay, minus b1 bar plus x bar all squared. Okay. Then lastly, we now have x22 minus a2 bar, then minus b2 bar plus x bar all squared. Yeah, I think that's the idea in this case. That's the idea here. Okay. So all we just need to do is to get out all these things. Um, so for interactions, right? So you're taking 1, 1, 1, 2. So if you take 1, 1, 1, 2 like that, the n should be 5, I think. Let's see how that works again. Yeah, for interactions, right? We have 4 groups, so it means that n in each case is 5. So we can just take, because that is common, right? But usually, right, this should actually be I think it's better to go down that way. Man, this is a lot, but let's see. Okay. I think this is better. This is better to make it for accuracy's sake. So this should actually be n, you know, this should be n. This is n11 multiplied by all that, then plus n12, okay? In alignment with all this, then this should be, so the n goes in. So this is n21. Interestingly, in this case, everything is 5. But it doesn't have to be. That's why I'm trying to ensure that I didn't just gloss over that. Then this can be n22, plus. So in short, so when we add all this together, this is our SSAB. So let's do that carefully. Okay, first, let's list. We already know that it's an interesting case here that everything is this, all the ends are the same. So we know that N11, trying to color code, N11 minus, is equal to N12 is equal to N21 is equal to N22, and all of that is 5. So we can factorize that N out already. Then the next thing is we need x11 bar equals x11 bar. Okay, that's 86.2. That's what we got at first. X12 bar is 87.6. X21 bar is 78.4. Then x22 bar is equal to 84.6. And then lastly, x bar itself is 84.2. Okay, that's from the very first step where we got all those things. Yeah, 86.2, 87.6, 78.4, and 84.6. Whereas the overall mean is 84.2 here. So with this now, we can put everything together. It's a lot. So we can now say SSAB. Of course, since everything is 5, we can factorize the 5 out. So all the N11 and everything is 5. So we can just call it, it's 5. So just say 5 into, then we start with the first one. X11 bar. X11 bar is 86.2. 86.2 minus A1 bar. Oh, we also need A1 bar, B1, all the A1, blah, blah. Wow. Ah, so this is A1 bar. Let's go for that, right? We need all that too. So A1 bar is equal to something, A2 bar is equal to something, B1 bar is something, and B2 bar is something. Let me see if I can bring all of them at once. So let's go back there. So A1 bar is okay. So 86.9, 81.5, 86.9. So this is 86, 86.9, 81.5. I guess this is 86.3 and 86.1. Just to be very sure, let me confirm those two. 86.3, 86.1. Yes, that works. Okay. So now we have everything together and we go on. Thankfully, this is the last sum of squares, but it's the most serious. So x11 bar minus a1 bar. So a1 bar now is 86.9, then minus b1 bar. So b1 bar is 86.3 plus x bar, which is 84.2. All of this squared, right? Yep, that works. Then, but of course, if the 5 is not common, so you have to multiply inside, you have to just multiply this one by its own end, but all the ends are the same. That's why the 5 is outside. So pay attention to that. The next one is x12 bar, x12 bar minus a1, x12 bar, that's 87.6 minus a1 bar, that is 86.9 again, minus, I believe this should be B2 now. B2, B2. Yep, that's B2 plus X bar. B2 bar is 86.1 plus 84.2 all squared. Then the third layer is X21. So X21. So X21 bar is 87.6 minus A2 bar now. That's 81.5 minus B1 bar, that's 86.3 plus 84.2 all squared. Okay. Then we have the last layer, which is X22 bar. X22 bar, that's 84.6. 84.6 minus A2 bar, that's 81.5 minus B2 bar, that's 86.1 plus 84.2 all squared. Okay. Right, so SSAB, SSAB. Well, we can still take the pain to compute this step by step. So we have 5 into, so I'll just take the squares out one after the other, and then sum and multiply by 5. So now the next is 86.2, 86.2 minus 86.9 minus 86.3 plus 84.2, all of that raised to power 2. All of that raised to power 2. Okay. 86.2 minus 86.9 minus 86.3 plus 84.5. 84.2 rather, all squared. That is 7.84. This is 7.84. That's the first one. The second one is 87.6. This is 87.6. 87.6 minus 86.9 minus 86.1 plus 84. 87.6 minus 86.7 minus 86.1 plus 84.2 all squared. So we have 1.44. That is the second one there. We have 87.6 minus 81.5. 87.6 minus 81.5 minus 86.3 plus 84.2 all squared. That is 16. This is 16 as the third one. Lastly, we have 84.6. 84.6 minus 81.5 minus 86.1 plus 84.2 all squared. And that is again 1.44. Okay. So SSAB again is equal to 5 into, okay, we add up all of that now. That is 7.84 plus 1.44 plus 16, 1.44 plus 16 plus 1.44. Okay. So this is 26.72. Again, 7.84 plus 1.44 plus 16 plus 1.44. That's 26.72. That multiplied by 5, that is 133.6. SSAB is 133.6. All right, so that's the end of the sum of squares, but that is not the end of the whole story. Okay. We are well over an hour. This will probably be the longest video I've ever made teaching maths. But let's see how that goes. Yeah, so SSAB turns out to be 133.6 for me. Okay. Um I think I want to check this third one. Is it really correct? Because it's the biggest, so I am curious if it's actually what it should be. So let me check that again. So I have the third one, 87.6 minus 81.5 minus 86.3 plus 84.2 raised to power 2. It's 16. Okay, that's fine. So SSAB is 133.6. Now that is, so all this SS, sum of squares now, that is just step, that is step 4 of um two-way ANOVA. So now we go to step 5. So step 5. So what does step 5 entail? Let's see that. Step 5. Um okay, now we need the mean squares now. Oh, is it the mean squares? Okay, I think we still need one kind of sum of squares though. We have sum of squares for interaction. Okay, I think we still need the error sum of squares. Okay, that should be step 5. Will that be it? Let me see. Would it be, there's something like error sum of squares. Let's see that. What is next? Error sum of squares, most likely. Let's be sure of that. Error sum of squares. Okay, yeah. So there's still a number 5 error. We have done 4 so far. There's a number 5 error. Yeah. Okay, so not step 5 yet. Still under sum of squares. Still under sum of squares. So we have 5. Sum of squares. Sum of squares for error. That is SSE. Sum of squares for error. SSE. And this actually measures, it measures the unexplained, variability, the unexplained variability within each combination, of factor levels. Okay. Thankfully, this one does not require serious computation. It's just sum of square error is sum of square total minus sum of squares for factor A minus sum of squares for factor B minus sum of squares for interaction. So it's just subtraction all the way. And that makes things pretty easy. So I'll just go for that straight up. SSE is equal to, what is sum of squares total? Sum of squares total again that we got. That is 453.2. That is our SST. 453.2. Okay, is 453.2 minus SSA. What is SSA again? SSA is 145.8. SSB is 80.2. Okay, so 145.8 minus 80.2. Then lastly, SSAB, which we just found, is 133.6. SSAB is 133.6. 133.6. So that's sum of squares for error. So again, don't forget SST is this, SSA is this, SSB is this, and SSAB is that. So that finally SSE is equal to that whole thing going on there. So that's 453.2 minus 145.8 minus 80.2 minus 133.6, and that is 93.6. So sum of squares for error is 93.6. And that ends step 4, which is talking about sum of the whole of step 3. No, that's the whole of step 4. That's calculate the sum of squares. So sum of squares total, sum of square A, sum of square B, sum of square AB, and sum of square for error. Then we go for so things are getting down gradually. So let's say, so the next thing, okay, before we even go, we have to calculate the step 4. Okay, this is actually, so in this case now, this is like my step 5. I think it's step 5 for me now, because step 4 is what I've just completed, sum of squares. Okay, so that's my step 5 now. So step 5 is the next thing. Step 5. So let's go for my step 5, which is calculate degrees of freedom. We need the degrees of freedom. Calculate degrees of freedom. Degrees of freedom. That is DF, right? So that's step 5. Step 5. Okay, so here now, say sum each sum of squares has a corresponding, we have 5 sum of squares now. So each of them is going to have a corresponding degrees, a corresponding degree of, is it degrees of freedom? Degree of freedom. So each one has that. So the first one, again, we can do all this itemization. 1, total degree of freedom. There's a total degree of freedom, and that is n minus 1. N is the total number of observations. So that would just be, total number of observations is 20 in this case, I believe. I think so. Okay, let me just write this out. Then the number 2 is number 2. Okay, let me just write that now, all the formula, then I'll just fix all the values also. So okay, I guess I have to do the meaning also. So n is the total number of observations, total number of observations. I think it's 20 in this case. Then number 2 is, okay, I guess let me just fix everything at once. So to avoid confusion, because there's a lot to deal with. There's a lot. Okay, so degrees of freedom. Degrees of freedom for total. Well, I think that should be 20. That should be 20 minus 1, and that is 19. So you can call that DFT. That's total degree of freedom. Then we can have degree of freedom for A. Okay, degree of freedom for A. Degree of freedom. So we can say factor A, degree of freedom. Okay, so that's, can call that DFA, and that is simply A minus 1. So A is the number of levels in factor A. Okay, so number of levels in factor A. That's easy. A has just 2 levels, so we have 2 minus 1. So the degree of freedom, so DFA is 1. So then the third one is, of course, factor B, degree of freedom. You can call that DFB. So that will be B minus 1. And again, B is the number of levels of factor B, which is just 2 also. Number of levels for factor B. Again, that is 2 minus 1, which is simply 1. Okay. Then we have the next one, interaction. So number 4, factor B, degree of freedom. Sorry, interaction degree of freedom. Sorry, interaction degree of freedom. That is what you can call DFAB, and it's simply given as A minus 1 into B minus 1. Of course, that is 2 minus 1 times 2 minus 1, which is 1 times 1, and that is simply 1. So DFAB is also 1. Then number 5 in degree of freedom, that is the error degree of freedom, which you can call DFE, and that is total observation minus AB. Total observation minus AB, and this is total observation, as we already, okay, total observation is 20, like we saw before. Okay, so I mean, that's total observation. So total observation minus AB, so this will be 20. A is 2 levels for factor A, 2 levels for factor B. That's 20 minus 4, and error degree of freedom is 16. So that's step 5 now. Calculate the degrees of freedom. So now we go for, I mean, with all we have done now, the worst is over, I want to believe. So let's go for the mean squares. Okay. Step 6. Step 6. Step 6. Calculate. Step 6. Calculate the mean squares. Calculate the mean squares. Like I said, the worst is already over. So again, we have mean square for factor A, that is MSA. So that's simply given as MSA equals sum of squares for A divided by degree of freedom for A. So sum of squares for A that I got is do I still remember? Okay, I think we can extract from here 145.8. 145.8, that's sum of squares for A. So that's 145.8. And the degree of freedom for A is simply 1. Okay, that means we have 145.8 settled. Then number 2, we need the mean square. The mean square for factor B. Mean square for factor B, that is MSB. So of course you expect MSB to also be SSB divided by degree of freedom for B, which is, so my SSB, sum of squares for factor B, is actually this guy, 80.2. 80.2. So again, 80.2 divided by 1, that's simply 80.2 easily. Then we have number 3. We need mean square for interaction. Mean square for interaction. That is MSAB. MSAB. And MSAB is simply SSAB divided by degree of freedom for AB. Okay. That is my SSAB is 133.6. So that's 133.6, 133.6, and DFAB again is 1. That is simply 133.6. Then we go again to step 4, mean square for error. Mean square for error, that is MSE. So here, MSE is equal to sum of squares for error divided by degree of freedom for error. So that is my SSE is SSE. Okay, my SSE is 93.6. 93.6. That's 93.6 divided by 16. 93.6 divided by 16, that's approximately something. 93.6 divided by 16. 93.6 divided by 16. That is, oh, I think it's, can we say it's a perfect value? That's simply 5.85. 5.85. That's the sum of squares for error. Okay, I think that with that we've finished up with step 6, which is the mean, to calculate the mean squares. We've done all the mean squares for A, B, the interaction, and the error. So now we go for the F statistics. F. Okay, so we have step 7, calculate the F statistics. So again, we have to do for each step. So for factor A, we simply have f of A to be MSA divided by MSE. Each one will be divided by MSE. So MSA, guess I want to take that down. So f of A is MSA. So you can see each step leads to the other. MSA is 145.8. So 145.8 divided by MSE, which is 5.85. Okay. So that's approximately, so 145.8 divided by 5.85. 145.8 divided by 5.85, and that is 24. That's approximately 24.9. Okay, so that is FA. Then, so we go for F statistic for factor B. So for factor B, the class type, factor A again is the teaching method. So for factor B, we have MSB divided by MSE. And that means that for F statistic for B is MSB now is 80.2. That's 80.2 divided by 5.85. That's approximately 80.2 divided by 5.85. 80.2 divided by 5.85, and that is 13.7. Okay, that is FB. Then the third F statistic is most likely, yeah, for interaction. So we say for interaction, for interaction, which is AB in this case. So for interaction, we have, let me take it down. FAB is MSAB divided by MSE. So mean squares for AB divided by mean square for error. So mean square for AB is 133.6. That's 133.6 divided by 5.85. 5.85. So 133.6 divided by 5.85. That is 22.8. 22.8. Okay, gradually coming to a close. Okay. The next thing, of course, once you calculate our test statistic for ANOVA is what you call the F statistics. So now we need the critical value. We need the critical value. So let's talk about the F critical values. That should be like that's step 7 now. So step 8. Step 8. Step 8. Find the F critical values. F critical values. Okay. So this is, so using F table for significance level 0.05. So again, we have okay, I mean, what exactly are we looking for? I think we have to check that out. So first of all, right, to interpret, compare the F values to critical values from the F distribution using significance level, often 0.05, right? So we have to start with factor A. Factor A. Okay. So for factor A now, we already got the FA. We already got that to be 24.9. So FA is 24.9. That's the test statistic. That's FA, right? 24.9. So now we need F critical. So we can now say FA critical, if you like. FA critical. What should that be? That's the question. FA critical is actually, that has to be F 1 degree of, I mean, F. Okay, I'm trying to really figure out what that should be. Okay. Yeah. So FA critical is, okay. FA critical is I'm trying to see, but I think we are comparing degrees of freedom here. So it's looking like A minus 1, N minus AB. That's what it's looking like to me. So doing 1 minus 16. So each of them, right? So this is simply, so critical value for F16, F1 comma 16, right? So it's more like we're saying, aha, I think we're looking for degree of freedom for A and degree of freedom for the error. So comparing that together, the value is approximately 4.49. Okay. Yeah, I think that's how it goes. So for factor B now, so this is 1, 2. For factor B, we already know that f of B is what we computed up there. F of B is 13.7 approximately. 13.7. Got that. So FB critical now. FB critical is more like F of degree of freedom for B, comma, degree of freedom for error. And that is also approximately 4.49. So 3 for interaction, AB, for interaction AB. Okay, for interaction AB, right? We already know F of AB, we computed up there, is 22.8 for interaction. That's 22.8. So if we now say critical, FAB critical is now F of degree of freedom for AB, then degree of freedom for error. And that is approximately, okay, this is still F1, 16, right? So again, this is F1, 16, which is still approximately 4.49. So all of them are 4.49. So that is step 8 is done now. Then we can go for the final decision. So that's step 9, I believe. Yeah, step 9. Step 9. So make final decisions. Make final decision. Okay. So 1, go for factor A. Factor A. So, I mean, in all the cases, right, we can see that all the test statistics are greater. Yeah. Yeah, everything is greater. Like FAB is greater than, all the values are greater. All the calculated statistics are greater than the critical values. So for factor A, right, we see that F A actually, which is equal to FA, which is equal to 24.9, okay, is actually greater than FA critical, which is equal to 4.49. So what does that mean? So we just reject. So because the test statistic is greater than the critical value, so we reject the null hypothesis. Reject the null hypothesis. And what that simply means is that there is a significant difference. So factor A is teaching method. So there is a significant difference between teaching methods. There's a significant difference between teaching methods. So it means teaching method 1 is definitely producing a different result from teaching method 2 between teaching methods. There's a significant difference teaching between teaching methods. Okay, so that goes for factor A. Now for factor B, number 2, for factor B, what do we have? F of B, I mean point 1, FB rather, is FB is 13.7. FB is 13.7, and it's surely greater than FB critical, which is 4.49. Again, same thing. We reject the null hypothesis. The null hypothesis will be something like there's no difference between the teaching methods. There's no difference between the class types. There's no difference, and then there's no significant interaction. Those are the three hypotheses, the three null hypotheses, so to speak. And then the alternative will just be to counter all of that. So here, because the test statistic is greater than the critical value, again, we reject the null hypothesis. Reject the null hypothesis. And what that simply means is that there is a significant difference. There is a significant difference between class types. So it means that if you teach in the lab or you teach in the lecture room, the results are significantly different. Of course, we don't know which is better, but we just know they are different. That's the idea here. Then we go for step 3. I mean, no, point 3 now, talking about interaction between interaction A-B, that's interaction between teaching method and the class type. So interaction between teaching method and class type. Again, we see that the test statistic FAB is approximately 22.8. Yeah, 22.8. Again, that's bigger. So 22.8 is greater than FAB critical. FAB critical again is still 4.49. Okay, it's greater. And once the test statistic is greater than the critical value, it means we have to reject the null hypothesis. So we reject the null hypothesis. So reject the null hypothesis in all the 3 situations here. Reject the null hypothesis. And what that simply means here is that there is significant interaction. There is significant interaction effect between teaching methods and class types. Okay, so reject the null hypothesis in the 3 situations. Okay. All right. So I mean, with all this now, we can just reach a conclusion. So in conclusion, in short, right? In conclusion, okay. These results suggest that teaching methods combined with class types this result suggests that teaching methods combined with class types have joint effect on test scores. In addition to each of teaching methods, and class types, influencing test scores. This is by far the longest video I've done teaching math, I believe. So, I mean, if you have come this far, you've really tried. Thanks for staying the course. It's almost 2 hours. If you have not subscribed to this channel, you want to surely subscribe. And you want to hit the notification bell so you can always get alerted each time a new video is released. Then don't forget to comment. Tell me any topic you'd like me to teach. And also, if you have a question to solve, you can also let me know by commenting. Then, of course, don't forget to like and share so that more people can have access to all this great learning. Till I come your way again, have a great time. Bye.